Have you ever looked up at the night sky and wondered, where did it all come from? How did this vast expanse of stars, planets, and galaxies come into existence? It's a question that has captivated humans for millennia. From ancient civilizations mapping the stars to modern astronomers peering through powerful telescopes, today, the prevailing scientific explanation is the Big Bang Theory. This groundbreaking theory has revolutionized our understanding of the universe. This theory describes the universe's evolution from an extremely hot, dense state billions of years ago. Imagine a time when everything we know was compressed into a singular point. The Big Bang Theory is not just an idea, it's a comprehensive model that explains a multitude of cosmic phenomena. It's supported by a wealth of observational evidence. Scientists have gathered data from various sources to piece together this cosmic puzzle. This evidence comes from many sources, including advanced telescopes and space missions. We see it in the expansion of the universe. Galaxies are moving away from each other, indicating that the universe is still growing. We observe it in the cosmic microwave background radiation. This faint glow is a remnant of the early universe, providing a snapshot of its infancy, and we find it in the abundance of light elements. The proportions of hydrogen and helium in the universe align perfectly with predictions from the Big Bang Theory. The Big Bang Theory is a journey through time. It takes us back to the very beginning and guides us through the universe's evolution. It's a story of the universe's birth and evolution, from the formation of the first atoms to the birth of stars and galaxies. And it's a story that continues to unfold today as we explore the cosmos. Each new discovery adds a chapter to this ever-expanding narrative. In the next section, we will journey back to the very beginning, to the singularity where it all started. Join us as we unravel the mysteries of the universe's origin. Imagine a point so small, so incredibly dense, that it contained all the matter and energy of the universe. This point is beyond our everyday comprehension, a place where the very fabric of space and time is twisted and contorted. This point, known as the singularity, is where our story begins. It's a concept that challenges our understanding of reality itself. We are talking about a time approximately 13.8 billion years ago, a moment so distant that it stretches the limits of our imagination. At the singularity, the laws of physics as we know them break down. Gravity becomes infinitely strong, and space-time curves infinitely. We can't describe what happened before the Big Bang. The concept of before loses its meaning in the face of such extreme conditions. The singularity represents the limit of our current understanding. Scientists and physicists are still grappling with the mysteries it holds. From this point of unimaginable density, the universe burst forth in an event we call the Big Bang. This was not just a simple explosion, but the birth of everything we know. It wasn't an explosion in the traditional sense. There was no sound, no fireball, just a rapid expansion of space itself. Instead, it was an expansion of space itself. Galaxies, stars, and planets would eventually form as space continued to stretch and grow. This expansion continues to this day. The universe is still growing, with galaxies moving further apart from each other. In the next section, we will explore the early stages of this expansion and the formation of the first particles. These particles would eventually come together to form the building blocks of everything we see around us today. In the first fraction of a second after the Big Bang, the universe was an inferno of unimaginable heat and density. As space expanded, the universe cooled. This cooling allowed for the formation of the first subatomic particles. Quarks, the building blocks of protons and neutrons, came into existence. Electrons, with their negative charge, zipped through the early universe, and other fundamental particles joined the cosmic dance. The universe was a whirlwind of creation. It transitioned from a sea of energy to a soup of fundamental particles. This era set the stage for the formation of the elements we know today. As the universe continued to cool, a remarkable process took place: Big Bang nucleosynthesis. During this period, protons and neutrons combined to form the first atomic nuclei. The universe was still too hot for atoms to form. Electrons remained free, creating a fog that scattered light. But within the first few minutes, the basic building blocks of matter were in place. The universe was primarily composed of the lightest elements, hydrogen and helium. This primordial abundance of hydrogen and helium is still observed today. It provides strong evidence for the Big Bang Theory. Section 5. Cosmic Echoes, the cosmic microwave background radiation. As the universe expanded and cooled further, a crucial transition occurred. Electrons combined with nuclei to form neutral atoms. This event, known as recombination, had a profound effect. The universe, once opaque, became transparent. Light was now free to travel across the cosmos. This first light, released about 380,000 years after the Big Bang, continues to travel through the universe. Today, we observe this ancient light as the cosmic microwave background radiation, or CMB. It's a faint glow, invisible to the naked eye, but detectable by our instruments. The CMB provides a snapshot of the universe in its infancy. Section 6. From gas clouds to galaxies, the formation of structure. The early universe, though vastly smoother than the cosmos we see today, was not perfectly uniform. Tiny fluctuations in density, amplified by gravity over millions of years, provided the seeds for structure formation. Regions with slightly higher density attracted more matter. These clumps of matter grew denser and hotter, eventually collapsing under their own gravity. This process gave birth to stars, star clusters, and the first galaxies. These early galaxies were smaller and more irregular than the majestic spiral and elliptical galaxies we observe today. Over billions of years, galaxies interacted and merged, shaping the large-scale structure of the universe. Section 7. A universe in motion. Hubble's law and the expanding universe. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that galaxies are moving away from us. Moreover, the farther away a galaxy is, the faster it appears to be receding. This observation, now known as Hubble's law, provided the first direct evidence that the universe is expanding. It's like dots on a balloon that's being inflated. As the balloon expands, the dots move farther apart. Hubble's law has profound implications. It suggests that the universe was once much smaller and denser. It provides compelling support for the Big Bang Theory. Section 8. The Unseen Universe. Dark Matter and Dark Energy. While the Big Bang Theory successfully explains many features of our universe, it also presents some puzzles. One of the most significant is the discovery of dark matter and dark energy. Dark matter doesn't emit, absorb, or reflect light. We can't see it directly. However, its gravitational effects are evident in the rotation of galaxies and the motion of galaxy clusters. Dark energy is even more mysterious. It's a hypothetical form of energy that permeates all of space. It's believed to be responsible for the accelerating expansion of the universe. Section 9. The Fate of the Universe. 3 possible endings. In this chapter, we will explore the 3 most widely discussed theories about how our universe might ultimately meet its end. The discovery of dark energy has profound implications for the fate of the universe. This mysterious force, which makes up about 68% of the universe, is driving its accelerated expansion. The universe's ultimate fate depends on the balance between the inward pull of gravity and the outward push of dark energy. This cosmic tug-of-war will determine whether the universe will expand forever, collapse, or tear itself apart. One possibility is the Big Freeze. This scenario envisions a universe that continues to expand indefinitely. If dark energy continues to dominate, the expansion of the universe will continue to accelerate. Galaxies will move away from each other at an ever-increasing rate. Galaxies will be pushed farther and farther apart, leading to a cold, dark, and empty universe. Stars will burn out, and new stars will no longer form, resulting in a lifeless cosmos. Another possibility is the Big Crunch. This theory suggests that the universe could eventually stop expanding and start contracting. If the gravity of all matter in the universe were to overcome the expansion, the universe could collapse in on itself in a reverse Big Bang. This would result in all matter being compressed into a singular point. A third possibility is the Big Rip. This is perhaps the most dramatic and catastrophic of the three scenarios. In this scenario, the expansion of the universe becomes so extreme that it tears apart all matter, from galaxies down to atoms. Eventually, even the smallest particles would be ripped apart, leading to the ultimate disintegration of the universe itself. Section 10. Conclusion: the Big Bang Theory and the ever-evolving universe. The Big Bang Theory is one of the most successful scientific theories ever developed. It explains a wide range of observations, from the abundance of light elements to the cosmic microwave background radiation. However, the Big Bang Theory is not the final word. Cosmology, the study of the universe, is a dynamic field. New discoveries are constantly being made, challenging our understanding and raising new questions. The universe is a vast and mysterious place. The Big Bang Theory provides a framework for understanding its evolution, but many mysteries remain. As we continue to explore the cosmos, we can expect even more surprises and a deeper understanding of our place in the universe.